Hello, I am Dr. Paris von Lockett, and today I'll be talking to you about the difference between solid elements and beam elements when trying to solve beam problems. It's an interesting problem that's actually buried in the physics of the problem and the way that we set up our analytical solutions and the way that we would set up a solution in what's called elasticity theory, which is a higher level class. The two solution methods have different assumptions built into them. The assumptions from beam theory are that it's long and slender. The assumptions from elasticity theory are that you just have small strains, like in beam theory, but you do not need the long, slender assumption. Plus, in beam theory, we actually throw out the idea of transverse shear, largely because it doesn't add a lot to the beam stress if you have something that's long and slender. That adds to the normal stress, I should say, that bending stress. But if the beam is not long and slender, then transverse shear is important, and that's what we'll see in these simulations. So this lecture focuses on the accuracy of solution of beam problems using either solid or beam elements. The topics for this lecture are beam element types and solid element types, the gauging of the accuracy of your solution, utility of beam elements, and after this lecture, it's important that you can judge when to and when not to use beam elements, understand the concept that geometry of your part can affect the solution, and it's important that you understand the concept that the degree of discretization can affect your solution. And by degree of discretization, what we mean is how many elements do you break up a solid body into? The more elements you have, typically your solution improves, but there's some caveats to that which we'll discuss later in the class. So in these slides, we'll go over a case study where we look at the simulation results of a model that's modeling a long, slender beam, and we'll do it with beam elements and we'll do it with solid elements. Beam elements are defined as a single line representing a path of a beam with the cross-sectional moment of inertia applied only as a theoretical calculation along the path. What does that mean? Well, that means we're generating line segments, but we're making an assumption that each of those line segments acts as a beam, and it's, I guess you should say, it's controlled by the boundary conditions on either end. So it could be fixed, built in, simply supported on one end. The other end, likewise, can be fixed, built in, simply supported. But if it's in a frame structure, then the other ends are beholden to whatever it's attached to. Solid element types in this case are used are tetrahedrons that recreate the model geometry, and they act as a one-to-one representation. What that means is that we discretize the beam into small elements and small chunks, and then we analyze each of those chunks, and we put the solutions for each of those chunks back together to see what the whole beam does. Whereas if you're using beam elements, you just assume that you've got one long beam or one long beam between boundary conditions. The beam elements offer a speed improvement, which is why they're actually used. They greatly reduce the number of degrees of freedom, that is the number of things that your problem has to solve for, but they're often questioned for accuracy over solid element types, but we'll show that in certain applications they work just fine. So here's our setup. We've got a 10mm diameter body, so it's all the way across, uniform circular cross section. It's loaded on one end with 100 newtons. On the other end, it's built in, so it's a cantilever, and we're looking at lengths between 20 millimeters at the low end, 400 millimeters on the long end. So we have a length to span ratio of 2:1 at the low end and 40:1 at the high end. And from these results, the maximum displacement and maximum stress values were collected for comparison to the analytical equations for cantilever beams. The mesh element sizes used for the solid studies is set to 1.33 millimeters. Now that's going to be important because get a picture in your head of what 1 1/3 millimeter looks like if you're breaking up a 20 millimeter beam into those sections versus a 400 millimeter beam. And the smaller beam, many fewer sections, and the larger beam, you'll have more. For this study, we also use the following analytical equations that we talked about last time. Our maximum deflection is delta equals FL cubed over 3EI, which is your standard cantilever formula. Also, for the maximum stress, we have FLR over I, which is FL which turns out to be your bending moment, times r, which is the radius, but the radius is also the maximum distance from your neutral axis, over I, which is your second moment of inertia. We can also plug in our modulus of elasticity and what the cross-sectional moment of inertia actually is for this beam, and we need those as we've determined in COMSOL to make our weldment profile for I and to apply our material for E. All right, so let's compare the solid element solution to the beam element solution for this problem. I'll let you take a look at the table on the right as I move myself out of the way. In general, when looking at data, it's a good idea to examine the table first to see what it's showing you in the columns. So our first column is beam length. We go from 15 millimeters all the way out to 200 millimeters. Our second column is the analytical solution. It goes from something very small, 11/10,000ths of a millimeter, all the way out to 2.5 millimeters. Our third column is the beam element solution. It goes from 14/10,000ths to 2.5. And then our solid element solution, which goes from 6/10,000ths all the way out to 2.5 millimeters. Now, if we look at our percent errors are very high for both the beam and the solid at our 15 millimeter length. 20% for the beam, 94%, so almost double for the solid element. But you can see that these quickly drop off. Once we get to about a 4:1 aspect ratio, we're down to about 3.5% error in both cases. Once we get to an 8:1 aspect ratio, we're down to about 2/3% for our solid element and about 1% for our beam. So the beam deflection results agree with the analytical solution within 5% for length to span ratios greater than 4:1 and accurate within 1% for ratios greater than 7:1. The solid element deflection results would agree with the beam deflection results as well. All right. Now we can also look at the comparison between solid and beam type elements for stress. If we look at beam length on one axis in our table, going from again 15 to 200, we look at the analytical solution and then compare that to the beam solution and the solid element solution. We can check our percent errors, and in general the percent errors are low across the board, especially for stress. The percent error is around 0.1% or so, or a few hundredths of a percent, and our percent error once we get off the smallest beam length is around 6% or less for the solid elements for stress. So the beam element stress results are identical to the analytical solution pretty much for all the tested model lengths, and the solid element stress results vary largely across the range, but they remain within about 8% of the analytical solution. And when you take a finite element class, they'll explain to you possibly why this would happen. And one possible reason is that in the beam element, what do we know? We know that any cut section has to be in equilibrium, and that equilibrium helps define the governing equations. Because of that, everything's always going to be in equilibrium, so the stress you solve for is going to be the same stress that you'd get in the analytical solution in your beam elements. For the solid elements, when you eventually begin to look at solutions for finite element methods, when you take that class here, what you'll see from the mathematics is that the equilibrium equations are only satisfied in an integrated sense. Because they're only satisfied in an integrated sense, you can have variations in the solution with respect to the actual analytical result. And some will be a little bit higher, some might be a little bit lower, depending on where you actually sample that solution with respect to your beam. But if you were to integrate over some whole face, then the whole face would then have to satisfy equilibrium, and the whole face then would probably be closer to the analytical solution than we have here. Well, as close as it could get, given that the solid solution is going to differ somewhat. So another way to look at this error is to examine our beam length on the x-axis here on this chart versus our y-axis of percent error. So if we plot it, the yellow line is for our solid elements, the blue line is for our beam elements, and we can see clearly as the beam length gets longer, the beam elements show improvement. And we would expect that. We know from beam theory that it has to be a long and slender beam. So when it gets very long, for a fixed span, that length of span begins to increase, the beam elements actually do better in terms of percent error. As we move to the left, as our beam length gets lower, our length of span decreases and the error gets higher. And you can see where that 4-to-1 and that 8-to-1 break are, which limit the percent error that we had in those beam elements. For our solid elements, however, you can see that, yes, as we increase our beam length, the error gets better, and as we decrease our beam length, the error gets worse, but they're not subscribing to beam theory. So why does this happen? To understand why this happens, we have to think about how the beam is discretized into these tetrahedral solid elements. And what do we know? Well, we know that there's a characteristic length for those elements set to 1.33 millimeters in this study, and because of that, we can actually calculate some approximate length of beam per discretization. By that, we can then determine how many divisions there are along the length of the beam. If we know it's 1.33 millimeters along the length, and we know the fixed length of the beam is 50, 100, 150, or 200, then we can scale that to the number of divisions. And what we see here is that as the number of divisions along the beam increase, we get lower error. And that is a characteristic of the finite element method. The number of elements in the mesh is an important factor in the accuracy of a solution. In general, the more elements you add, the closer you're going to get to a numerical result that approximates the real world, or I should say approximates the final converged value for your model. The solution will tend to something it will eventually solve for if you were going to some infinite number. And the idea is, how many elements or how many divisions do we need to reach a fraction of that solution such that our error is small enough that we're okay with it. The difference in the solutions between solid mechanics and beam problems can boil down to how we look at and understand the underlying physics of each problem. Beam theory, and thereby beam elements, are attempting to solve the beam equation with given boundary conditions. That equation is given by EI, where E is our modulus and I is our moment of inertia, times the fourth derivative of y, our displacement, with respect to x. And that's equal to W of x, which here is our distributed load. We solve this fourth order equation with respect to our boundary conditions, and that gives us the solution to our beam. The origin of the difference in solution stems from the underlying mechanics of each problem. The solid elements are attempting to solve the governing equations of solid mechanics, which include, for a linear study, three equations of equilibrium, del dot sigma equals 0, where del is the gradient operator dotted on a stress matrix sigma, six stress-strain relationship, sigma equals d epsilon, which transform our strains into stresses, and six strain displacement equations, epsilon equals 1/2 del u plus del u transpose, that transform our displacements of each point into strains. Here, sigma contains our six stresses in x, y, and z, and the mixes xx, xy, yz, yy, yz, zz, etc. And similarly, the strain matrix, epsilon, contains our six strains in the x, y, and z directions, and the mixes. And the vector u contains our three displacements in x, y, and z. Like I said, d contains our elasticity constants. As you can imagine, this is a much tougher problem to solve than simply solving our fourth order beam equation. So what conclusions can we draw? Well, beam elements have an uncertain accuracy for deflections below a length span of 8-to-1, so you want to be higher than that, and that's a caveat of beam theory in general, even the analytical results, so that's not surprising. For stress calculations, beam stresses use the analytical solution for the stress, so the results would be the same, right? So we would expect to have similar results from the FEA because we use the beam equations and we're solving the differential underlying beam equation. Solid elements show similar accuracies to beams for deflections when the length spans are greater than 4 to 1, but higher errors for stresses. What does this mean? Well, if you're over 4 to 1 in length, solid elements are still okay because what are they taking into account for? This transverse shear, which does not exist in beam elements. That long, slender approximation means that the bending stresses, those normal stresses, are going to dominate, but the farther you get away from that, the more important transverse stresses are. So transverse stresses are picked up by solid elements, but not by beams. However, reducing the solid element mesh size would compensate for this error. So as we saw, as the beam got longer, yes, the solution error decreased for the solid elements, but this is partly due to the fact that we had more elements along the length of the beam. So solids can be trusted for length span ratios of less than 8 to 1, where beam calculations and the analytical equations become invalid. So the solid elements, like I said, pick up this transverse shear, so they don't necessarily require you to have a long, slender approximation or long, slender situation, but what you do need is to have more elements divided for that geometry. You need more divisions to make sure that there's more elements within whatever span you're dealing with. The big takeaway is that beam elements in this case solve 1,000 times faster than their solid counterparts. And that's because there are fewer degrees of freedom in beam elements, which makes them a simpler problem to solve. Why is that useful? Well, if you can imagine design iterations, if you're trying to optimize something, or if you're trying to just do proof of concept within FEA and use that to iterate on next models, you'd want this to be as fast as possible. And that's why beam theory and other structural elements were developed. Finally, for larger, more complex beam structures, the inaccuracy from beam elements are offset by a reduced design cycle and solve time. So yes, you might have some small errors, but you're able to refine, get closer and closer and closer to the final design that you want. And once you reach that final design, then you can begin to do what's called a mesh convergence. And as we've shown here, you just increase the number of elements for a fixed beam length, and that actually will improve your solution as you go along, as much as you can. Well, thank you for participating. Hopefully you've learned a little bit about the comparison between solid elements and beam elements, and you have an idea of when to choose one versus the other, what sort of geometries are amenable to long, slender approximations for beams, and what would be better suited by solid elements, and you have an idea of the concept that at times you may need to divide your model into more and more elements to ensure that your solution converges to a value that's closer to what the real solution would be, or closer to an analytical solution if you've got something to compare it to. All right, thank you again for participating. Take care.